What we want to explore right now, just out loud, is the Seebeck effect. Because this months ago brought me down a really complicated trail of thought in data centers for where or what might happen in the intercepts of where they're used to thermal coupling, the radiation, the thermal energy that's getting released from the data center. What I've been wondering is if you create a protocol that's so smart that it's knitting with the thermal energy, it's configuring it. It's still allowing it, of course. It's still a radiator. It's just managing how it goes through that field, and in effect, it's compiling and focusing it into the necessary avenues or course corrections for something to be done. And so that's what's interesting is thinking of that Seebeck effect, where you have two ends of a thermocouple at different temperatures, and there's a resultant electricity flowing from the hot metal to the cold plate. And what's interesting is there seems to be a fall off. It seems to diminish over time. And so it ended up being an interesting spot to imagine a sensor drift in something that either makes it work better or worse. And what could be, the core to processors and semiconduction in the field around it, to where that lattice ends up being, a signal front that's very useful. And so I think that trace route to what could be mass affected in data centers through those laminar flow channels, basically assembling compositions of nutrients in suspension, whether it's just air, atmosphere, and clean scapes. The air's been filtered, and then maybe the right kind of nutritional ensemble is added to it, to where they're weaving together some complex formula for where they have a huge return on that investment of basically using that energy, organizing it, using a percentage of that thermal output and organization. And one of the derivatives of that is then, if needed, the thermal system, the subsystem could be, made more efficient. So that becomes all scalar avenues of uh, inspirational utilization of the ice mechanism. So you're thinking of Masonic valve trains and atmospheres, and what could be done by just compute fielding tetrahedral field mechanisms uh, in a simplified logistical landscape. So signals correlate, and this kind of field thermal couple becomes an averaging that influences just right for the maybe the Mobius effect that might be a derivative of having that system. So say it's a Mobius strip where it's just doing an orthogonal transition of energy, right? So it's almost like going towards that little CAD quadrant where it's just showing the corner of a CAD file. Sorry, my nose started getting itchy. I'm in a dry state. And so in this corner of a CAD file, there's it's the reference anchor, and that scape of energy is uh, such that range of interactions up there and the thermal state of focused energy down here with the tendrils of energy and influence could be a computable range, like the holographic projection where it can project the landscape out from that kind of an array set into the environment, where you're having a distributed field display across a scalar, like a CRT monitor of what's happening across that logistical landscape. So the digital field, trying to think of ways for computers to interact with these volumetric processors where the field can be measured, quantized, reflected, refracted, whatever the right term is for the arrangement of elements in resonance and energies that could be passed through those materials through different ranges of the temperature. Uh, we want to know what is good. And one of my favorites is the cube. And in the cube, this is inspired by a fluidic solution where in the right kind of resonance of vibrational mechanisms, the atomics are thermally just right for a little bit more heat, maybe the cavitation effects or something like that, sets the right amount of thermal density with pressures and hydraulics, and this weaves together a lattice, a three-dimensional intercept, and somehow we formulate a weave of quantum dots to either silver nanotubes or maybe carbon trusses, and we use actual nanotubes or graphene sheets, or just the standard silicon, oxygen, silicone, daisy chain, SIOSI, I should just say, daisy chains that intercept, and the variable extent to where these nests reside in a field in the logical intercepts of energies to which can interact on that system can then be different ways of deriving a range of standard scientific, you know, uh, accuracy in those scalar fields that are basically those MEM gear sets. And someone who had created a proposal here in Upworks mentioned, or I saw somewhere, working in MEM gear sets, and so that's going to be an important array. Is what can be conducted easily? How would you simplify the description of what that mechanical system that you put together does? And because some of the utilities, like ultralight phones, that's just like a semiconductive screen, or just having these three-dimensional meshes that have EM field energies to help arrange molecular laminar flows of fluid or atmospheric systems in low gravity or natural gravity environments, affords a really wide diversity. You use gradients and gravities, and uh, you can get isotopic divisions, uh, the Seebeck effect. One of the things that seemed worthwhile was seeing how a processor could apply enough order to the chaos of a Seebeck system to make it either stay functional longer or act as a tuner for the amount of influx. And what does that mean? What could be gained from that kind of a derivation of space-time? It was something that's tough to think of at that intercept of reflective material surface and the actual volume that the material inherently is comprised of, a reflection of the field energy. I don't know. You tell me.